Hello, it's dumplet here. Here's an item on algebra. Find the minimum value of x cubed minus x plus 2 all over y plus z plus y cubed minus y plus 2 all over z plus x plus z cubed minus z plus 2 all over x plus y, where x, y, and z are positive real numbers. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. Now this might be one of those Olympiad type questions where we have to supply a proof, and the first thing to notice here is that, okay, we have positive real numbers. Now the second thing to think of is, to realize here is that the given is actually symmetric. So what do I mean by that is that I can switch up x, y, and z's in. I can take any permutation of them, and it's still going to be equivalent. So more likely than not, whenever we have a symmetric given, the minimum value, it's always going to happen in x equals y equals z. Again, this is just usually, but I think I can safely say that 90% of the time, you can take x equals y equals z and kind of get the minimum value, or at least the extreme value, one of the extreme values that way. So again, when given with this item, it's just we just really start with some trial and error and hope to kind of see what's the minimum value, and then go on with the solution. So okay, if x equals y equals z, then all of the terms is going to look something like k cubed minus k plus 2 all over 2k. So just substituting all of them to be k, and you're going to realize it's just 3 times this value of k cubed minus k plus 2 divided by 2k. So I'll just focus on one of them. So whatever is the minimum value of this one, I'm just going to multiply it by 3. Alright, so this one, I can factor a k in the first 2 terms. That's why I split it into these 2 terms. So k times k squared minus 1 divided by 2k, and then a plus 2 over 2k over here. So simplifying, we're going to get this k squared minus 1 divided by 2 plus 1 over k. So this 1 over k actually motivates me to do this next step, which is to separate, well, aside from removing this minus 1/2 to here. So what I did here is k squared over 2 plus 1 over 2k plus 1 over 2k. So I splitted this 1 over k into 1 over 2k's. It's because of a k in the denominator, and well, it is kind of expected from the start. We have like positive real numbers x, y, and z, so we immediately think of those. For example, the AMGM inequality, probably the most simplest of inequalities out there, and this is actually a very common manipulation in AMGM. We have a k squared here, so we kind of want 2k's in the denominator, so we can use AMGM. So we're going to use AMGM in the first 3 terms, and we'll see that it's going to be greater than or equal to 3 times the cube root of 1/8. So if I multiply these 3 terms, it's going to be 1/8, and well, cube root of 1/8, that's 1/2. So the first 3 terms, it's going to be greater than or equal to 3/2. So this entire thing would be greater than or equal to 3/2 minus 1/2, so 1. So apparently, again, these are just all guesses, but it is a pretty good guess for now because of the fact that the given equation, the given expression is symmetric. So from our initial assumption, I think all of these terms would be greater than or equal to 1. So I think if we can kind of make some assumptions right now, the minimum value here is going to be 3. So, but it's important to note that the equality is going to happen when these 3 terms are all the same. So the k squared over 2, the 1 over 2k, and the 1 over 2k here are the same. So let's just try to get the equality case before we move on to kind of with the solution to the question. So k squared over 2 equals 1 over 2k. We're going to get here that k cubed is 1. So, well, k is a positive real number because of the given. So k is equal to 1. So apparently the equality case is at x equals y equals z, and they're all equal to 1. So if I substitute x, y, z, both equal to, all of them equal to 1, I will get the minimum value of 3. Again, this is just a guess, but you're going to see later probably the motivation behind all of these substitutions and the claims that I'll be making towards getting the proof for the solution, for the question. Alright, now first things first, it is annoying that we have this minus x, minus y, and minus z. Those are not really common in a lot of the inequalities out there. So for example, the AMGM, you don't use, there's typically not a minus sign. And actually a lot of the more famous inequalities, for example, the Cauchy-Schwarz inequality, the Titus lemma, the Hölder's inequality, and actually there's a lot of inequalities out there, but most of them don't have this minus sign. So the first claim that I'll be making is to kind of rewrite all of these terms into something else. And the claim that I'll be making might not be obvious at first, but it is the following. So I'll be claiming that x cubed minus x plus 2 is greater than or equal to 2x. Again, I'll be claiming this true for x greater than 0 because, well, we have the restriction in the given that x, y, and z are positive real numbers. So essentially, it suffices for us to prove this one. So x cubed minus 3x plus 2 equals 0. Now the left side, hopefully we can factor that, and yes, we can easily factor that using our knowledge in just algebra, and we realize that 1 is a root, 1 is a 0 to the left side. So we can use the synthetic division or just the long division, totally up to you guys. So I'll use the synthetic division, it's a little bit faster. So if I were to divide this x cubed minus 3x plus 2 by x minus 1, because 1 is a root to this left side, 1 is a 0 to the left side, I'll be getting x squared plus x minus 2. And we know this is further factorable, so aside from the x minus 1 that we got, we're going to factor this one, the x squared plus x minus 2, and this is actually factorable into x minus 1 times x plus 2, greater than or equal to 0. So essentially we just kind of have to solve a cubic inequality. But that's no problem because, well, we have negative 2 and 1. We just simply use the number line to kind of help us here. All right. Substituting values greater than 1, let's just say 2 as a test point, it is going to work. And 1 is obviously part of the solution here because 1 is a root, so it is going to be greater than or equal to 0. So we can safely say that values from 1 to positive infinity is going to be true. It's going to satisfy this inequality. And you guys can figure it out here that, for example, if I substitute 0, it is also going to work. So values from negative 2 to 1, it is going to work indeed. Now if I substitute negative 3, you guys going to realize that it's not going to work. So left region will not work. So the solution to this cubic inequality will be x in the range negative 2 to positive infinity. And, well, since x greater than 0, so since the positive real numbers is a subset of this one, so the claim is indeed correct. Now, we could have proven this using calculus, which is not really common in a lot of Olympiad questions, but we can still use calculus by checking on x cubed minus 3x plus 2. So for example, f of x equals x cubed minus 3x plus 2. The first derivative gives us 3x squared minus 3, and the second derivative gives us 6x. Now it's important to note that, again, x is a positive real number, and using this one, you can already tell that the concavity is going to be, it's always concave up. The graph of f of x is always concave up. So all the critical points that I'll be getting should give us at least a minimum value. And if I were to make f prime of x to be 0 here and solve like the turning points, to find the turning points here, I'll be getting x equals negative 1 and 1. But again, we're dealing with x greater than 0. We're just going to ignore the negative 1 for now. And apparently, the minimum value of f of x for x greater than 0, it happens at x equals 1. Now, if x equals 1, that's going to give us f of x being equal to 0. So the minimum value of f of x is 0. So we can get the same result. Since the minimum value of f of x is 0, x cubed minus 3x plus 2 is going to be greater than or equal to 0, at least for all real numbers, all positive real numbers x. All right. Now, after we make this claim, what's going to happen next is this. So x cubed minus x, the given expression, it is pretty long, but the given expression, since we know that x cubed minus x plus 2, that's going to be greater than or equal to 2x, so the first term becomes like this. And similarly for the second and the third term, it becomes 2y and 2z in the numerator. So the given expression would be greater than or equal to this expression over here. And we can factor the 2 out, and I think some of you guys might be familiar with this expression inside the parentheses. X over y plus z plus y over z plus x plus z over x plus y over here. It is a pretty well-known inequality, and it is the Nesbitt's inequality. So the Nesbitt's inequality, it states that for any positive real numbers x, y, and z, the minimum value of literally this expression, it's going to be greater than or equal to 3 halves. And when does it happen? It happens at x equals y equals z. So, well, 2 times a value that's going to be greater than or equal to 3 halves, it's literally going to give us greater than or equal to 3. And there we have it. We don't need to solve for the equality case anymore since we found it in the start, but from start to finish, starting from the motivation and some of the assumptions we can kind of use based from like other symmetric inequalities, there we have it. We have the minimum value of the given expression to be equal to 3. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.